Yeah, sure. Do we have authors from Oasis of Cooperation? I thought I saw Peter. Yes, Peter, do you have anything that you can share?
Yep. I'll share my screen. Cool, you can see that? Perfect.
Yes.
Cool, so I'm going to be presenting a poster on our work on Oasis of Cooperation, which is an empirical evaluation of reinforcement learning in the iterative process dilemma. So here we wanted to investigate cooperativity when the players locally have an incentive not to cooperate, such that they can choose to defect locally, even though like both players defecting causes a bad outcome for all players. So we started by training our RL agents in a single agent case, first training it some fixed policies to see what kind of policies developed. And so we trained against a policy which played the tit for tat policy, but then after a random turn started defecting. And then we showed that for some regions of the hyperparameter space, the agents developed strategies similar to tit for tat, but in other regions of the hyperparameter space, they learned to always defect. Then we moved on to multi-agent training, and we showed that these agents in general are unable to find these cooperative Nash equilibria, even if such a Nash equilibria does exist. So if you have a random game length, it's possible that your agents cooperate, but these reinforcement learning agents were unable to find this. Then we moved on to seeing if we could instill good behavior in our agents. So we pre-trained these agents against fixed policies to instill certain behavior in the hope that this would affect the behavior they developed in multi-agent training. So when we trained them to first always cooperate, they quickly fell into this always defection mode. While when we trained them to develop strategies similar to tit for tat, they remained somewhat cooperative. Cool, that's it.
Thank you so much, Peter. I think I saw Fanqi for the second paper.
Okay.
Yeah, please go ahead and share your screen.
Okay. Hello, my distinguished colleagues. I am Li Fangqi from Shanghai Jiangtong University, and it is an honor to be able to present our work entitled Leveraging Multitask Learning for Unambiguous and Flexible Deep Neural Network Watermarking in this SafeAI event. So with the DNN being deployed widely, it is necessary to protect them as intellectual properties for both commercial benefits and legal accountability. This process is usually done through the watermark. So it is unlike the multimedia domain and another series of security targets such as the unambiguity, robustness against the tunings, and the flexibility has to be considered. However, the established DNN watermarking schemes can hardly fulfill all these requirements, which facts hinders their practical application in industry. To address these challenges, we propose the multitask learning sign that utilizes multitask learning for DNN watermarking. The ownership evidence is encoded into the labels of an extra task, where that is functioning parallel to the primary task. The training of the extra task on the proper regularizers can be seen as introducing a specific pattern of noise into the DNS parameters, which can be decoded as the ownership evidence by the watermarking tasks backend. So this would enable the multitask learning sign to package various types of DNN architectures for different tasks. So we also conduct experiments on tasks, including image classification, semantic segmentations, and also the segmental classification for the NLP. They also verify the privilege of our scheme compared to concurrent method. Oh, that is basically the idea.
Thank you, Fanqi. And Pradip, good to see you here. Can you share your screen?
Can I share my screen?
Yeah, sure, please go ahead.
Yes, yeah. Yes, so my ideas regarding human-in-the-loop learning for safe exploration through anomaly prediction and intervention. So we know that in autonomous driving, demonstration data or historical data is usually used as a starting point for training the driving policy, because it's not really effective to start with a complete self-exploration kind of point of view. But then to improve on this driving policy, the agent will have several rounds of iteration of training and the driving as well. But when you do that, we have to ensure that the exploration is in a safer territory. So safer exploration can be made possible with the use of human in the loop. And that's what we are trying here in this approach. So I will just explain with the diagram quickly. So initially you have some data stored with historical data and demonstrations. You collect some features from them. You extract the features, and basically you find out the data points which are seemingly anomalous. And then you have a human in the loop present continuously during the first initial phase to classify the samples as either erroneous or correct. And if it's a correct sample, then we can use that directly to train the policy. If it's erroneous, that we can use that to train a block called as anomaly predictor. So the anomaly predictor basically makes use of these erroneous samples and also the environment dynamics to predict anomalous events before in advance. So once this is trained to a sufficient degree, then we can go to the next level where you have exploration by the agent, and the agent always chooses actions which are less risky because it's able to predict in advance what's going to happen for each action it takes. So it can choose lesser risky actions. So there are three varieties. You can have like safe self-exploration, where there's just one agent, and the agent looks at all the possible actions and chooses the least risky one. If it's continuous, then you have to discretize in this case. Then you have learning from intervention, where the agent follows its policy and it knows the risk for its own action. If it's highly risky, then it passes over control to another actor. But then in joint execution, you have both the oracle and agent who's present. And based on which actor's action is less risky, we choose that actor. So these are the three different variants that we want to try. Thank you.
Thank you, Prajit. And shall we so Leopold, are you here?
Yes.
Yes, when you're ready, please share your screen.
Okay, I hope you can see it.
Yes.
Okay. Hello, I'm Leopold. I'm excited to present you our concept safety-aware reinforcement learning by identifying comprehensible constraints in expert demonstration. Let's dive directly into the paper. Our approach consists of two main components. In the first, we derive safety rules from expert demonstrations, shown as yellow in the concept scheme. To do this, we record the behavior of an expert, for example, a human, and obtain expert demonstrations consisting of a set of trajectories. On these, we apply the card algorithm and obtain a decision tree. To obtain the most relevant and compact rule set possible, while maintaining transparency and explainability, we consider the path of the decision tree as association rules. This allows us to use the metric support and confidence as hyperparameters to filter the safety rules. The two graphs on this slide show how the hyperparameters successfully influence the number and length of rules in a rule set. For the second component, we consider the following slide. We use a safety layer with access to the safety rules, green in the concept scheme, to integrate the rules into the decision process. It checks proposed actions and performs corrections in case of rule violation. Results show, among other findings, that through the safety layer alone, a completely untrained agent can achieve the performance of the expert, but also show how dependent the performance is on the quality of the expert demonstrations. Thank you so much for having us.
Thank you, Leopold. So now we will head on to the coffee break. Feel free to stay in the chat and just chat freely if you want. And our next session will start on 10:15. So if you want to stay here, just feel free to come back later.